Bivariant data is characterized by paired measurements, which are usually graphed as a scatterplot. Ordered pairs are plotted on a horizontal and vertical axis. While you may have heard previous math teachers refer to the horizontal axis as the independent axis, we will be plotting the explanatory variable here. The explanatory variable helps explain how the dependent or response variable is changing. The response variable will be plotted on the vertical axis. We will use the term response over dependent when describing a variable's response to a treatment. Whenever we encounter a scatter plot from here on out, we will be interested in describing a number of its qualities or characteristics. Mainly, we are interested in its linearity, how closely the graph resembles a straight line. For now, we will call this the best fit line. Shape, direction, and strength are terms we will use to describe the linearity of a scatter plot. Let's look at some graphs that demonstrate these characteristics. Now that you've had a chance to examine the graphs, let's discuss some common trends. Some of the graphs have a positive trend, while others display a negative relationship between the horizontal and vertical axes. We can also comment on the relative strength of the linear relationships. For example, graph A shows a positive trend and a strong linear relationship. Comparatively, graph B has an equally strong relationship but has a negative trend, while graph C shows a positive trend but overall a weaker linear relationship. Beyond a qualitative discussion of linearity, a more quantitative or mathematical formula can be used. The correlation coefficient, or R, of the plotted points describes numerically the strength of the linear relationship. Closer inspection of the formula shows it is simply the sum of the z-scores of the coordinates of each point. This brings into question the use of this formula when dealing with non-normally distributed data, since z-scores are calculated based on the mean of the explanatory and the response data. More on this later. For now, let's assume the data to be tame. Now, let's take a look at how to interpret an R value and how that might relate back to our previous graphs. In general, a correlation coefficient can take on any value between and including -1 and +1. So, as a relationship back to our graphs, a positive or negative value is consistent with the slope of the line. It should be noted this is the only connection with the slope. The value of the slope has no relation to the R value. The strength of the linear relationship is displayed by the absolute value of the correlation coefficient. A value of 1 tells us that every data point falls perfectly on the line, positive or negative. And R equals 0 says there's no better relationship between the variables than a set of random numbers. Care must be taken when verbally describing the strength of the linear relationship, but the following guidelines can be used with caution. Since the calculation of the correlation coefficient is dependent upon the mean of the data, R must not be a resistant statistic. Indeed, the addition of an extreme data point can greatly affect the shape of the best fit line and the value of the correlation coefficient. Take for instance this mild-mannered graph which has an R value of 0.981. Here the blue line represents our best fit line. However, when an additional point is added to the data set, the correlation shows a dramatic change, not only in the value, but in its sign as well. The result shows up in the best fit line. This type of data point is called an influential point because its presence changes the graph dramatically. What can we say and what can't we say about correlation? The value of R shows how strong the linear relationship is between two variables. It is tempting to take this too far and assume that the explanatory variable is causing the response variable. The big thought here is that correlation does not imply causation. Let me explain with an example. Assume I perform a study which gives me a very strong correlation coefficient. The study is one in which I measure the reading ability of all students in the school district while also measuring their height. When plotted, it becomes clear that the taller the student, the better their reading ability. A tempting conclusion would be that height dictates reading ability. Maybe even more tempting to imagine a school wishing to increase their scores in reading by taking all their students and stretching them out on some sort of medieval rack. But alas, we understand there is a lurking variable called age, and we have to recognize that height is not the cause of reading ability. Okay, here are some points to review as we finish up this lecture on bivariant data. If you have questions, bring them to class, and we'll see you soon.